Welcome. The title of today's lecture is Scattering in Quantum Mechanics, but it has a subtitle, A Deeper Look. Now exactly what do I mean by that? Let me point out that scattering is a standard topic in quantum mechanics texts and quantum mechanics courses. In fact, it starts from the very first course in quantum mechanics where you study scattering from a one-dimensional potential and goes on to more advanced courses where you study things like scattering from a central potential or perhaps even scattering from asymmetric potentials and so on. Now, given that this is the standard staple in every quantum mechanics course, why am I at all talking about this here? And what do I really mean by this set of words? A deeper look. Now, to understand that, let me first take a quick look at scattering as we studied in our very first quantum mechanics course, scattering from a step potential. Note that in today's lecture we will essentially study scattering from a step potential in one dimension because that is where all the real complications can be illustrated reasonably simply. If you are familiar with the topic, you would know that scattering in higher dimensions, especially scattering in central potentials, involves some special techniques like phase shift studies or spherical waves studies and so on. We are really not talking about those in the deeper look part here. They are technicalities which can be mastered rather straightforwardly. Although, of course, they are difficult topics in their own, there are no real surprises there. The surprise that is there in scattering theory, at least a surprise for most people who have done just an elementary course, is there even in the very first topic in this theory that they do, the step potential. Now, before I talk about exactly what the surprise is, let me quickly recapitulate for you what you all have learned in the very first course in quantum mechanics. This is scattering from a step potential. So a textbook typically says this: you have a potential where V, the potential is 0 for negative x, and you have another region, region 2 in my drawing, where the potential V is a constant, V0, a positive constant, at least for the time being, for x greater than 0. Now, the way in which this is solved in our first course is the following. You solve the time-independent Schroedinger equation, which of course is, as you all know, minus h cross square by twice m d2 psi dx2 plus v of x psi equals e psi. This is of course the equation for any time-independent potential in one dimension. And because the potential has two different forms in the two different regions, we break up the equation into two pieces. In region 1, where x is less than 0, v is 0. So what you really have is d2 psi dx2 is minus twice me by h cross square times psi, and we can rewrite that as psi double prime plus k square psi, where k is related to the energy E by, it's not really E1, it's just E, energy E by h cross square k square by twice m is E. In region 2, on the other hand, there is a potential. The potential is actually V0, a constant. So the equation becomes psi double prime plus k prime square psi equals 0, and k prime is given by h cross square k prime square by twice m equals E minus V0. Now, the equations themselves are pretty easy to solve. In region 1, psi of x can be given by a sinusoidal solution, a e to the I kx plus b e to the minus I kx, where x is less than 0. And in region 2, here we are assuming that E is greater than V0. Region 2, the solution is again sinusoidal. Psi of x is c e to the I k prime x. There would have been a d e to the minus I k prime x term as well, But we set that equal to 0 because once you put in the time dependence e to the minus I et by h cross along with the psi of x's in the two cases, it's easy to see that the first term here represents a wave going to the right, the second term represents a wave going to the left. Same here, a right going wave, a left going wave. Now, since our original setup that we are talking about is one in which we are imagining a particle is coming in from the left, very far from the left, somewhere here, and coming in and impinging on the barrier, and then on the step, and then getting either reflected or transmitted. This term would not be a physical one. This would tell you that there is a particle coming in very far from the right and moving towards the barrier, which of course doesn't make sense in this scenario. So we dropped this term, we set d equal to 0. Now, these two are solutions to the Schrodinger equation, the time-independent Schrodinger equation, in region 1 and region 2 respectively. However, putting them together does not give you a solution to the full Schrodinger equation, which has to be valid everywhere, including at x equal to 0. And in order that the equation be valid at x equal to 0, what you need is the function, wave function, and its derivative be continuous at that point. Or we can put these two demands together and demand the continuity of d dx of log of psi, which is of course psi prime by psi. And a very simple calculation immediately gives us that this will lead to k times a minus b by a plus b equals k prime. So this can be easily solved using component to dividendo to give you b over a as k minus k prime by k plus k prime. And continuity would have told you that c is equal to a plus b. So c over a is given by 1 plus b over a, which is twice k by k plus k prime. Now for an interpretation of these results. The wave in region 1, a to the ikx plus b to the minus ikx, can be directly thought of as a sum of two terms, an incident wave and a reflected wave. The incident wave is simply a to the power ikx, where we have multiplied it with the time dependent factor e to the minus I et by h cross. Together, this clearly shows that this is a wave which is traveling to the right. So, a particle coming in from the left, impinging on the barrier, should be represented by this. And the corresponding probability current density that we can calculate, J, for the incident wave, Ji, turns out to be h cross k over m a mod square. That's what you would get if you were to calculate the probability current density J from this. The reflected wave is, now this is a mistake, this should be b e to the power minus ikx times e to the minus iet by h cross. This is a wave traveling to the left. It is already to the left of the step and is traveling to the left. This is of course a reflected beam whose current density Jr is given by minus h cross k over m mod b square. And the transmitted wave, which is given by, again I don't know why I made these mistakes, but c e to the power ik prime x e to the minus iet by h cross, and the transmitted current will be given by h cross k prime by m c mod square. So, as the textbooks tell us, to find the reflection coefficient, which is essentially the probability that a particular particle is going to be reflected by the step, you have to divide Jr's magnitude by Ji. The negative sign in Jr simply shows that it's moving to the left. You get mod b by mod a whole square, the h cross k by m cancels, and you're left with k minus k prime by k plus k prime whole square. The transmission coefficient, the probability that the particle is going to be transmitted, is mod jt by mod ji, and there you end up with k prime by k into mod c by a whole square, which after a brief calculation works out to be 4k k prime by k plus k prime whole square. The great thing about this result is that if you add r and t, you do get 1, which you expect anyway, because the particle, once it's incident on the step, can either be reflected or transmitted. And that is captured by the fact that r plus t is 1. So this is the standard calculation that is done in textbooks, and this is what we learn in our very first course in quantum mechanics. But why do we then need a deeper look? Let me point out that this derivation has some very, very important gaps. The most important one of them is the following. You are solving the time-independent Schrodinger equation to get to this answer. But what TISE, the time-independent Schrodinger equation, describes are stationary states, states which do not change with time. The physical situation that we are talking about here is extremely different. We are talking about a particle which is coming in from way to the left, hitting the step, and then either being reflected or transmitted. This is an inherently time-dependent situation. It is not at all clear how it is possible that the solution to a time-independent Schrodinger equation, which describes a state which does not change with time physically at all, is going to actually talk about this scenario and give a correct result. So this is the real question. How can an explicitly time-dependent problem be answered by solving the time-independent Schrodinger equation? This is the central conundrum in scattering theory, at least the way it is presented in textbooks. Now, there is one more point, which is the wave function that we had obtained for x less than 0 is actually a sum of two terms, a to the power ikx plus b to the minus ikx, right? In our notation, we are not using k1, k2, we are just using k and k prime. So, this has a current which is given by J given by, there's a standard formula, H cross by M, imaginary part of psi star d psi dx. Now, this should not really be our Ji minus Jr. Actually, the moment you multiply psi star with d psi dx, you expect not only terms with A's and A stars to go together and B's and B stars to go together, you would also get cross terms in the multiplication. And here we have not taken them into account. Strictly speaking, what I should have said here is may and not will, for a simple reason. It does turn out that in one dimension, and that is why we have a caveat here, this statement that I made just now is not perfectly precise. In one dimension, if you calculate J by using this H cross by M imaginary part of psi star times d psi dx, what you get is H cross by M imaginary part of, this is psi star, then d psi dx will give you ik, a to the power ikx minus b to the minus ikx. And now you can easily split up this into two pieces. H cross by M, imaginary part, you take the ik and multiply this with this and this with this, you get a mod square minus b mod square. The phases cancel. In addition to that, you have one more piece, which is when you take this term with this term, the cross term that we were talking about, and this term with this term. Now I've got the signs wrong here, this should be minus and this should be plus. But that actually doesn't really make much of a difference to my final conclusion. For the simple reason that this thing in the bracket here is a purely imaginary number. It is the imaginary part of the quantity b star a, it is a twice ikx. Actually twice the imaginary part. So multiplication by I renders this purely real, and since we are looking at the imaginary part only in J, this part doesn't contribute. So in one dimension you do get H cross by M into A mod square minus B mod square for the J. So let me just take back what I said just a while ago. In one dimension, J does turn out to be Ji minus Jr. So, at least in one dimension, interpreting the two pieces of the wave on the left as incident and reflected may not be wrong in its own right. However, when we go on to higher dimensions, this result no longer works. Cross terms do appear. And so, in general, this is the problem with our standard discussion of scattering theory. How do we actually interpret the wave functions? And remember, these are time-independent wave functions basically. The e to the minus iet by h cross essentially is just an overall phase factor. How do we interpret those wave functions and get an answer to this problem of an inherently time-dependent nature? Now, most elementary textbooks tend to sweep these issues under the carpet. A few of the better ones, who do acknowledge that the problem exists, usually refer the interested reader to journal articles where the puzzle is solved. The solution is the following. The time-independent Schrodinger equation approach with this incident-reflected current split actually works and does give you the correct answer under some assumptions. But the reason why it works is quite non-trivial. Well, most readers will not have access to these journal articles, and even if they do, figuring out exactly what those journal articles are saying is quite difficult for a beginning student of quantum mechanics. Indeed, among all the books that I have seen, the only elementary textbook, a beginning quantum mechanics textbook, which actually addresses this issue quite directly and in some detail, happens to be the book by Ramamurthy Shankar, Principles of Quantum Mechanics. The rest of my lecture is essentially going to be based on what Shankar says. So, if you have access to the book and you are prepared to do some hard work with pen and paper, I would suggest that rather than watch the rest of the video, you can actually go and directly deal with Shankar's book itself. I do actually go a bit deeper than Shankar, not really deeper, but I do some calculations which Shankar has left essential as exercises to the students in some detail in the rest of the lecture, but I would still stress science is not a spectator sport, so it may be a good idea to get your hands dirty and work out the thing yourselves rather than rely on what I am telling you. That being said, let me now get into the actual details of how, at least in the case of one-dimensional step potential, a thorough calculation can be done for the actual physical situation which we are considering. But before we do that, we need a brief mathematical interlude. Now, most of you who are going to view this video actually already know these results, so you may skip the next few minutes and go ahead to when I start talking about the step potential again. But let me just still stress this for the sake of completeness. One result that we are going to need very, very strongly here is the result for the Gaussian integral. The integral of e to the power minus ax squared dx all over the real line from minus infinity to plus infinity happens to be square root of pi by a, where the real part of a has to be positive for this integral to actually converge and the value that we have written down on the right hand side to make sense. Now, the proof of this is something which is again pretty well known. You can of course reduce this to a gamma function by a substitution ax square equals t and then rely on the fact that you know that gamma half is root pi, but then the question could arise as to exactly how do we know that gamma half is root pi in the first place, and the answer actually comes from an alternative way of evaluating this integral. One such way is you can consider I square, I times I, where you write the same integral twice, once with x and the other time with y, as a dummy variable of integration. Now you can collect these two terms together and write this as a double integral over the entire plane, entire xy plane of e to the power minus a x square plus y square. We then move over from Cartesian coordinates and describe the same double integral in polar coordinates, where the measure for the area is, as you all know, r dr d theta. So now, in order to get the entire plane, what you need to do is let theta go all the way from 0 to 2 pi, all the way around, and let r go all the way from 0, its lowest possible value, to infinity. And that's going to give you the entire plane. Now this integral now becomes a very elementary integral to calculate. The theta integral is simply 2 pi, and the r integral can be calculated using standard fundamental theorem of integral calculus, and it works out to be pi over a, and therefore I works out to be root over pi over a. This of course is a pretty well known result. I am just stressing the proof here for completeness. Now what we will often need is a general Gaussian integral minus infinity to plus infinity of e to the power minus ax square plus bx plus c. So in the exponent you don't have just a quadratic term, you have the general quadratic polynomial, quadratic, linear and constant in x, and you are integrating that. The answer once again exists only when the real part of a is positive, and is given by root over pi by a e to the b square by 4a plus c. Now the proof of this follows from elementary algebra. You start with the exponent minus ax square plus bx plus c, take the minus a common from the terms involving x, and supply a 2 and a 1 by 2 of course to set up a completion of square. So we complete the square here, and this gives us an additional b square by 4a in addition to the c that you already had. So now what you are doing is integrating this expression, which is ultimately e to the power b square by 4a plus c, this constant factor, times an integral of e to the minus a x minus b by 2a whole square over the entire real line. Now shifting x by b by twice a, so that x minus b by twice a becomes your new dummy variable, immediately allows you to carry out that integral. This is nothing but the same integral as the one we had done before, and that gives you the root over pi by a in front. Now there's one catch which I still want to emphasize in this rather elementary derivation. Is this shift of variable x minus b by twice a, x bar or x prime or whatever you want to call it, is this justified? Now as long as b by 2a is real, you are just shifting a point on the real line to a neighboring point, and this will not cause any difference in the limits over which you are going to do the integration, the limits being minus infinity and plus infinity. However, if b by twice a had an imaginary part, and in most of our applications it will have an imaginary part, then the shifted line is actually no longer the real line. The shifted line is a line parallel to the real line. So basically what you are doing is you are actually integrating over this line, whereas the result that we had used a while ago is a result for the real line. I have shown the integral from minus L to plus L with a standard trick that in the end we are going to take L going to infinity. But are we justified in using the result for the green line here, the one on the real axis, the integral of e to the minus ax squared dx from minus infinity to plus infinity, for what we are really calculating here, an integral over the blue line, which is shifted either above or below depending on the sign of the imaginary part of b by twice a. Now, the fact that the result root over pi by a follows even for the integral about the blue line is simple to see. Basically, if you think of a closed contour where you go from minus L to plus L along this line above or away from the real axis, then close by a line here, go back along the real axis and close again by this, I get a closed contour. Now, the integrand, an exponential of minus az square plus bz plus c, where z is just a general complex number x plus iy, happens to be completely analytic in the region that is being enclosed by this closed contour. Therefore, the integral over this closed contour is 0. As long as the real part of A is positive, for both plus L tending to infinity and minus L tending to minus infinity, the integrand will be vanishingly small over these vertical lines, and those integrals, these two lines, will not contribute to the final contour integral. So that means that this integral along the blue line and this integral along the green line going from minus L to plus L will give you the same result, thus establishing that the blue line integral, the one that we are actually doing, gives you the same value as the integral over the real line, the green line integral in our picture. So root over pi by a is perfectly okay. Now, in addition to these results, I am just stating two more results which would be of some use later on, a bit indirectly. If instead of just an exponential of a quadratic piece you already had an x in front while integrating, the result can be established very easily by partially differentiating with respect to b, this expression, and you get root over pi by a, b by twice a times whatever you had before. So the integral without the x has been multiplied by b by twice a here. For the quadratic term in front, x squared to the minus ax squared plus bx plus c integrated from minus infinity to plus infinity, the result can be obtained by taking the negative of the partial derivative with respect to a, and after a bit of manipulation, this turns out to be 1 over a times half plus b by 4a into the original integral of the quadratic exponential. Now these two results we will need only peripherally. These are not really that important for the rest of our work. Now with these mathematical preliminaries out of the way, let us actually start following Shankar and working out how we should really solve the problem of a particle coming in from very far away, impinging on the barrier and then either reflecting or transmitting. The actual time-dependent situation is illustrated in the pictures that you can see on your screen right now. On the left, we are at time t equals 0. The same step potential that we described at the beginning of the lecture is present here as well. We have a particle which is coming in and is described by a wave packet. A confined region in space where the wave function exists describes the fact that the particle is more or less localized to some degree of certainty. Now, this wave packet is seen to be centered at x equal to minus a, and the packet is traveling towards the right, that is towards the barrier, with some mean speed. Of course, as you all know, the narrower this wave packet will be in space, the wider will be its spread in momentum. That's the uncertainty principle. So what we have here is a reasonably well confined packet, a narrow packet, narrow enough such that at this instant it's very far away from the step. The wave packet dies out very, very rapidly, well before it reaches the step. But at the same time, it's not so narrow that we cannot talk reliably about its mean energy. If the wave packet were very narrow, then of course its energy would have been spread out quite a lot and the mean energy would have been rather senseless. We do expect the particles coming out from, say, an accelerator to have a particular energy or an energy centered around some particular mean energy with a small variation. So that has to be kept in mind while we talk about this particular wave packet. Now this is the situation at t equal to 0. What happens when t is very large? Here we have said t is much, much bigger than t0, where t0 is a characteristic time that we are going to describe soon. At very large times, we expect that the incident wave packet would have already come, hit the barrier and split into two pieces. One piece would be traveling towards the left from the barrier. This is the reflected beam. And the other piece would be traveling towards the right. That's the transmitted part. So our job would essentially be to start with the wave function which is in the form of this narrow wave packet, calculate how it evolves in time, and check that at very large times t, you do get a situation like this out of the time evolution. And then, just by integrating the mod squares of psi r and psi t, we would expect to find out what? The probabilities of reflection and transmission are. Now, at t equal to 0, we need to start with a well-defined wave function. Actually, the physical situation demands that the wave packet has to be narrow in space, reasonably narrow in space. For mathematical convenience, more than anything else, we are going to assume that the incident wave packet psi I of x, this is at t equal to 0, so this depends only on x, is a Gaussian wave packet with center at minus a as described by this figure and with a spread given by sigma. So, it's described by exponential of minus x plus a whole square divided by 2 sigma square plus I times k naught x plus a, where k naught is the mean momentum of this wave packet. And of course, there is a normalization constant in front. Now, such a Gaussian wave packet centered at x equal to minus a with sigma can be described in Fourier space also as a Gaussian packet. If you carry out the Fourier transform of psi I x, you will get its momentum space decomposition, which turns out to be peaked at k0 and has a spread of h cross by sigma. To see that, what we need to do is take the Fourier transform of psi I x, that is phi I of k. The Fourier transform is carried out by multiplying by e to the power minus I kx and then integrating over all space with a factor of 1 by root 2 pi thrown in to keep the norms straight. And once you calculate this by plugging in the value of psi I, this is the integral you have to do. Note that the integral you would have to do is e to the minus I kx plus I k0 x plus a. What I have done is I have also thrown e to the minus I ka here in this inside the exponent and compensated for that with an e to the I ka, a constant outside. Note that the integral is with respect to x, so e to the I ka behaves like constant. After this, this is a standard Gaussian integral of the kind that we had described a while ago, with small a equals 1 over 2 sigma square and small b equals minus I k minus k naught. And c, of course, is 0. There is no term independent of k minus k0, independent of x plus a here. You have to realize that what we have actually done, although we have not stated that officially, is that we have gone over to the variable x plus a instead of x. That does not change either the measure or the limits. Now, using the formula that we had derived a while ago, you can easily calculate this, and this works out to be exponential. There is a b square by 4a term, and once you calculate this, you get minus sigma square by 2 k minus k0 whole square plus the I ka, which was outside, and the overall normalization constant after the cancellations works out to be sigma square by pi to the power 1/4. Note that this is a Gaussian centered at k0 and with a width given by 1 over sigma. So while we wanted sigma to be sufficiently small that the wave packet can be thought of as localized in space and was not spreading out all over the place, we must also ensure that it is large enough so that 1 over sigma is very small, the width in momentum space. And you want it to be very small compared to the mean wavelength or mean wave number k naught. which actually means sigma is much bigger than square root of h cross square by twice me, E being the mean energy of the particles that are coming in. So we have two apparently contradictory demands. Sigma must be much smaller than A and must be much bigger than 1 over k naught. However, this contradiction is really not a problem simply because the microscopic world is very tiny, and compared to that A, which is typically a macroscopic distance, even if it's as small as a millimeter or a micrometer, the distance from which the wave packet comes and hits the step, this condition can be easily satisfied. You can have wave packets which are so narrow that you can consider them to be well localized particles, and at the same time so wide that the corresponding momentum wave function is actually very narrow compared to the energy that these particles have. And what about the time t0 that we mentioned? That can be easily estimated simply by the distance a divided by the mean speed of the particles. Since the mean momentum is h cross k naught, the mean speed is h cross k naught by m. So time t0, the time at which the wave packet is supposed to arrive at the barrier, is ma over h cross k naught. Remember, what we are going to try to see is what happens when t, the time, is much bigger than this t naught. So long way after the actual collision takes place or actual scattering event takes place. Now, how do we proceed solving the problem? The steps that we need to carry out are as follows. First, we have to solve for the spectrum of the Hamiltonian p square by twice m plus v of x. That is, we need to find out the eigenfunctions psi e and eigenvalues e of the Hamiltonian. This is what we have to do in general to solve for time evolution for quantum systems, at least for quantum systems where the potential energy is independent of time, simply because the time independent Schrodinger equation, which gives us these eigenvalues and eigenfunctions, is the stepping stone towards a full-fledged time-dependent solution. Once we have the spectrum, we need to expand the initial wave function psi I in terms of the psi e's. In our present problem, the label k is a continuous variable, so instead of a summation, we have an integration over all possible values of k here, with coefficients which are of course k dependent. So we write psi I, rather than using e as a label, we use k as a label, so we write psi I as integral from minus infinity to plus infinity over k of psi k of x ak. Let me just stress once again, I am just suppressing the letter e from the label here. Psi kx means exactly the same thing as a psi e of k functions of x meant here. These are the energy eigenfunctions labeled instead of the energy E by the wave number k. Strictly speaking, the wave number k to the left of the barrier in our present problem. In order to find out the coefficients ak, what we need to do is simply calculate the overlap of these eigenfunctions psi k's with the incident wave function psi I. And now that we have all these coefficients, we know that each energy eigenfunction evolves in time by picking up a phase factor of e to the minus I et by h cross. Once we take this phase factor into account for each individual momentum or each individual wave number k, we can use that to find psi xt, the time dependent wave function. This is how you solve the problem of time evolution in quantum mechanics in general. But now that you have done this, what we need to check for is that at very large positive times, the wave function that we calculate does split into two pieces, a reflected piece and a transmitted piece. So we end up with two wave packets traveling in opposite directions. If it does, and the answer happens to be yes in this case, we can integrate the mod squares of psi r and psi t over all space to find out the probability that a particle will be reflected or transmitted. These are, of course, the quantities r and t, reflectance and transmittance, relevant for this particular scattering process. Now, of course, as we said, we need to know the spectrum of the Hamiltonian, and we have discussed the spectrum and how to arrive at it very briefly near the beginning of today's lecture. Also, there is something you study in first year quantum mechanics. The wave functions are given to be of this form. Psi kx is a times e to the ikx plus b e to the minus ikx. This theta minus x tells us that this part only contributes when x is less than 0, plus c over a e to the ik prime x theta x. This, of course, contributes non-trivially only when x is positive. This k is related to the energy E by E equals h cross square k square by twice m, and k prime and k are related to each other by this relation. We have already figured out what B by A and C by A are, and this is a complete description of a particular energy eigenfunction labeled by the wave number k. Complete, that is, up to a normalization constant. We still need to figure that out. For the time being, we are going to keep that as A. We are going to figure out what the appropriate normalization constant will be soon. Now, the next step, of course, is expanding. So we start with the initial wave function psi at x comma 0, which is, of course, psi I of x, and expand that in terms of psi k x's. And how do we find out the AKs, these coefficients? AKs are the overlaps, as we said, of psi k's with psi i's. That is, you have to take the conjugate of psi k and multiply that by psi I and integrate over all space. So if we take the conjugate of psi k and multiply by psi I, this is what you get. This ends up splitting into two integrals, in fact three integrals. One with e to the minus ikx term, the other with the plus e to the ikx term, and finally a term with e to the minus ik prime x. Note that the original psi k had e to the plus ikx here and e to the minus ikx here. The change in sign is obviously because you are doing a conjugation. Similarly, you had e to the ik prime x going with theta x in psi k. The conjugate has c by a's conjugate times e to the minus ik prime x. Now, we need to remember that our incident wave function psi I x is strongly peaked around x equal to minus a. So sharply peaked that the wave function vanishes long before you get to x equal to 0. On the other hand, its Fourier transform is also strongly peaked. In fact, the original wave packet has to be not so strongly peaked to ensure that this happens, and we have already argued that that can be done. The Fourier transform is strongly peaked around k equal to plus k0. Now this tells us that two of these integrals will actually not contribute to a significant degree. Firstly, psi I x is strongly peaked around x equal to minus a. This integral, despite being from minus infinity to plus infinity nominally, is only from 0 to infinity because of the presence of theta x. And that means that in the region where this integral is carried out, psi I x is nearly 0, so this integral is very, very tiny, and we can ignore that. On the other hand, if you try calculating this, what you are really calculating here effectively is the Fourier transform of psi I x at minus k. But psi I x has a Fourier transform which is peaked very strongly around plus k0. So for any negative value of k, the Fourier transform is going to be very, very tiny. So this term is going to also become very tiny. So ultimately the only term which contributes to a significant degree is the very first term. Because of the theta minus x, the integral will be actually from minus infinity to 0. You have the a star outside e to the minus ikx psi I x dx. Now, we do know what the integral would have been if it had been from minus infinity to plus infinity. That is exactly the Fourier space wave function or Fourier transform of psi ix. Note, however, that we are not very far away from that either. Although this integral is only from minus infinity to 0, psi I becomes so tiny by the time we get to positive x that you can replace the upper limit here by plus infinity, and that's not going to affect the value of the integral to any noticeable extent. So, once you carry out the approximation, this really becomes the Fourier transform or root 2 pi times the Fourier transform of psi I x. And we do know what that Fourier transform is. So, our ak, the coefficient that we are looking for, is given by root over 2 pi a star sigma square by pi's fourth root times exponential of minus k naught whole square sigma square by 2 plus ika. This, of course, is exactly the Fourier transform that we had calculated. Now, one important point. We have said that we need to expand our wave function, the incident wave function, in terms of the energy eigenfunctions. And the reason why this works, of course, is that the energy eigenfunctions form a complete basis for the space of wave functions. However, in order to form a complete basis, we need to take all energy eigenfunctions. What we have done so far is only consider energy eigenfunctions with energy E more than V0. We had not bothered to calculate the eigenfunctions with energy E less than V0 when we were talking about it, but such energy eigenfunctions are of course there. They do not contribute anything to transmission, again something we have learned in the first year course, but that doesn't mean that the wave functions are not there. However, the k value for such wave functions, the wave number of the real wave which is there on the left of the barrier, it only becomes exponentially decreasing to the right for E less than V0. The wave number here is much smaller than k0. And by the same argument that we had used to say that the reflected wave, which is essentially the Fourier component at minus k, is negligibly small, that argument can also be used to show that you will not expect contributions from these eigenstates with energy E less than V0 to a significant extent. So what we can always do is ignore such energy eigenfunctions and work only with energy eigenfunctions which are for E greater than V0, which is what we have done so far. So now that we have the expansion coefficients in terms of the energy eigenfunctions, we can find out the time evolved wave function by just plugging in the time dependent phase factor e to the minus iet by h cross. So that's all there is to it. Psi x0, the initial wave function was minus infinity to plus infinity ak psi kx dk. Each of these energy eigenfunctions pick up an e to the minus iet by h cross, and that is how you end up with an integral describing psi of x comma t. Now with our calculated value of ak, capital A star root 2 pi times this, etc., we have just plugged everything in, and then this exactly is what psi k of x is. Now, there are three pieces here, 1, 2 and 3, and these three pieces contribute to three distinct integrals. At t equal to 0, according to the arguments that we have given just a while ago, same kind of arguments, only the first integral contributes. So, you just have either ikx times this times e to the minus ih cross k square t by twice m, etc., etc. it's easy to see that if we want to get back psi I x at t equal to 0, the only way you can do that is actually to choose the a to be 1 over root 2 pi or a star root 2 pi to be 1, which is the same thing. And once you plug that value in of a as 1 over root 2 pi, this is what psi of x comma t turns out to be. This is the normalization constant after you put in the value of a, and this of course is the a of k apart from whatever piece goes in here. This is a time dependent phase factor. This essentially is a psi k of x. The 1 by root 2 pi which was there in the psi k of x has been absorbed in here. Now we need to take a look at the three integrals which we have here of psi, the wave function at time t, separately and try to interpret each one of them. So psi xt is of course psi 1 plus psi 2 plus psi 3, and let's look at these things one by one. The very first integral, psi 1, simply comes from taking all of this and e to the ikx dk. So what you get is theta minus x, which being a constant as far as the k integral is concerned can be moved out of the integral, into the normalization constant sigma square by 4 pi cube to the power 1/4. Then you have an exponential of minus k0 whole square sigma square by 2 minus ih cross k square by twice mt plus ik x plus a. The plus ikx plus a comes from these two terms. Now this is a Gaussian integral. Remember that we are integrating against k, and what you have in the exponent is a quadratic function in k. We can evaluate this exactly using our standard Gaussian integration formula, but to do that what I am going to do is I need to write this as a quadratic in either k or k minus k0. It turns out, not so much for this integral, but for the other integrals that we need to calculate, expanding in powers of k minus k0 is actually better. For this one, you can do it either as a polynomial in k or a polynomial in k minus k0. Both ways you are going to get the same answer. But this is slightly more convenient here and way more convenient for the other two calculations. So here, what we do is change everything to powers of k minus k0. This is already a power. The k square we write as k minus k0 plus k0 whole square, and then of course use the binomial theorem. The k here we write as k minus k0 plus k0. After we do that, all we need to do is expand out the things and then collect terms into quadratic in k minus k0, linear in k minus k0, and independent of k minus k0 pieces. Here is the quadratic piece. Sigma square by 2 comes from here, minus ih cross t by twice m comes from here. In the linear piece, x plus a comes from this term, minus h cross k0 t by m comes from this term, after we multiply by this. And finally, this piece is a term which is independent of k minus k0, which comes from this and this. So now we have an integrand which is of the form exponential of minus a x square plus bx plus c, where the role of x is being played by k minus k0. So here the red coefficient is the a, the purple one is the b, and the orange one is c. And this is something you can explicitly calculate. Root over pi by a is root over 2 pi by sigma square plus ih cross t by m. It is a minus b square by twice a by 4a actually becomes this, and this is e to the power c. So this is my first integral. Now it's obvious that this is the part that should correspond to the incident wave. And let's just take a look at this in some detail to understand why that is the case. First of all, it's obviously a Gaussian which is centered at x equal to x0 equals minus a plus h cross k naught t by m. This makes perfect sense because remember the particle we are describing is actually one which started at x equal to minus a and then was moving towards the right with a mean momentum of h cross k naught. So h cross k naught by m, mean velocity times t. That gives us a perfectly good result for the center of the wave packet. Also, and this is very important, at t equal to 0 this reproduces exactly theta I, which is why we chose a to be 1 by root 2 pi in the first place. What we have written here is, apart from the theta minus x, psi I xt, this psi 1 which we now identify as psi I, is g with center at minus a plus h cross k naught t by m and a sigma which is given by this effectively. And also it has a momentum k naught or wave number k naught saying that it's traveling to the right. Now, what happens when t is much bigger than t naught? That is, t is so big that h cross k naught t by m is way bigger than a. Then the center of this Gaussian piece would be at a large positive value. The center is at minus a plus h cross k naught t by m, and when h cross k naught t by m is much bigger than a, x naught is at a large positive value. So the Gaussian alone would have been peaked somewhere here, where this is x equal to 0. However, psi I x carries with it a theta minus x term. That means that for any value of x more than 0, this is going to vanish. So this psi I of x comma t vanishes for very large times. So the picture that we had of an incident wave starting at minus a, traveling to the right and vanishing at very large positive times is borne out by this piece. That tells us, of course, that our identification of this as psi I is perfect. Of course, when I say it vanishes, it's not the wave function that vanishes, it's only this piece that vanishes. Its role is taken up by the other two pieces, psi 2 and psi 3, which are what we are going to examine next. So psi 2, the second integral, also has a theta minus x and has this particular form. The one major difference from psi 1 is that there is a b by a there. The other major difference is, instead of e to the ikx, it has e to the minus ikx. So, this is what the integral becomes. This term is of course the e to the ika which was sitting there in the exponent. So, this is the full form. Now, once again, this looks like this is a Gaussian integral. After all, you have k's quadratic up here in the exponent. But what ruins matter somewhat is b by a itself is also a function of k. Since b by a is a function of k, strictly speaking, this is not a Gaussian integral. However, note that what we have said is the size of this exponent, which is dictated essentially by e to the power minus k0 squared sigma square by 2, this piece becomes very small when k stays far away from k0. Roughly, k0 plus minus 1 over sigma is the range over which k can be. Outside that, this term essentially drops off to 0. That means that since this b by a is a slowly varying function of k, we can replace it by its value at k0 and pull this out of the integral. The integrand here will vanish when you are far away from k minus k0 anyway. So given that, what we can do is simply replace b by a, which is a function of k, by b by a at k0, and after that the integral is very easy to calculate. Things will go almost in the same manner. It will turn out to be b over a k0 theta minus x times G, a Gaussian wave function, normalized Gaussian wave packet, whose center is at A minus h cross k0 t by m. So this looks like a particle which is coming in from x equal to A and moving towards the left. Now that might seem like a bit of a surprise. After all, at t equal to 0, this wave packet is centered at x equal to A. Whereas at t equal to 0, we know that the entire physical wave packet was to the left of the barrier. But that's really not a surprise, because remember, this is not the entire wave function. The wave function has a theta minus x in front. And that ensures that at t equal to 0, this piece is strictly 0. It becomes significant only when the Gaussian becomes significant for negative x, and that happens only at times exceeding ma over h cross k0, times exceeding t0, by which time the incident wave packet has gone and nearly struck the barrier, and the reflected wave packet is now starting to be born and showing its face to the left of the barrier. So what happens when you consider this at times much bigger than t0, ma over h cross k0? And the answer is simple. When you are at large positive times, the center of this Gaussian is at a large negative value for x, and that means the Gaussian essentially is non-zero only around that point. So theta minus x doesn't have much of a role to play any longer. You end up with the Gaussian traveling all the way to the left and traveling to the left. To the left because you have a minus I k0, which comes from this term. So this is our reflected wave. And how do we calculate the reflection coefficient? It's just psi r mod square dx is integral. And since the Gaussian piece is already normalized to 1, the theta minus x for large positive times does not contribute anything more than what the Gaussian has already done. You integrate and you find that the answer is simply b by a mod square, which here we have written in terms of the energy E0. This is just k minus k prime by k plus k prime square. Now, one question could worry us a bit. We have kept up to quadratic order pieces in k in the exponent, and that's how we got the Gaussian integral. What we have done for b by a, the coefficient in front, is that we have just replaced it by its value at k0 and pulled the whole thing out. Shouldn't we have, just for consistency, expanded b by a as a function of k also up to quadratic powers? Write b by a at k as something like some constant c0 plus c1 into k minus k naught plus c2 into k minus k naught whole square, at least up to quadratic power, because we are keeping up to quadratic power in the exponent, and then carried out the calculation. In fact, you could have carried out the calculation that way. We do know how to handle x times an exponential and x square times an exponential. Those are the results that we had just mentioned near the end of our mathematics interlude. It turns out that that's really not necessary. One important point is, a term in an exponent, of course, is way more important than a term which is just multiplying the thing. So retaining up to quadratic power in the exponent is actually not the same thing as retaining up to quadratic power here. You don't really have to retain up to quadratic power in the multiplying function. If you do not believe me, you can easily check this out simply by carrying out the integrals with k minus k0 and k minus k0 whole square here, something we have already done, and arguing that in each case, because of the fact that the original wave packet is reasonably narrow, you are going to end up with almost no contribution from those terms compared to the term that we have kept. So the answer to the question, should we have kept up to higher order terms in b by a, the answer is no. the sharp peak of the Gaussian essentially gives you a rather good approximation. You have the tools to calculate the thing explicitly and checking this out. I'm not going to bother to do that. If you really feel the need to check this out, you're welcome to carry out the calculation. With the calculation of R, the reflection coefficient, out of the way, the only thing that is left is to calculate T, the transmittance. Now we can get that very simply by using the relationship that T equals 1 minus R. Or we can get this directly from the definition of T, that is, take the transmitted wave function psi3 or psi t, whatever we call it, take its modular square, integrate that over all space. Now, let me try to convince you that both of these methods should give you the same answer. And the argument for that is based on a very simple property of quantum mechanics, the conservation of probability. If you are dealing with a Hermitian Hamiltonian, that is a potential energy term which is real, the integral of psi mod square over all space is independent of time. This follows directly from the time-dependent Schrodinger equation. We just write down the time-dependent Schrodinger equation, I h cross del psi del t equals minus h cross square by twice mt2 psi dx2, del 2 psi del x2, of course, plus v of x psi, and then you take its complex conjugate. Multiply the first one by psi star, the second one by psi, and subtract the two, and this leads, after a simple manipulation, to the result which you know as the equation of continuity for probability density. Del t of psi mod square turns out to be minus del j del x. This j is, of course, the same thing as h cross by m times the imaginary part of psi star del psi del x, the current density that we had used earlier in our first year course to figure out what the reflectance and the transmittance are. If we integrate this equation over all space, we end up with ddt of the integral of psi mod square is the same as the integral of minus del j del x over all space, and then this turns out to be minus j's value at plus infinity, subtracted from it is minus j's value at minus infinity. And since the current density is supposed to die down at infinity, with wave packets that will definitely happen, in this case you are going to get a 0 for this rate of change of psi mod square integral. Note that these are partial derivatives, but this one here, ddt, is a total derivative. It just says the psi mod square dx integrated from minus infinity to plus infinity does not change with time. Now this is something which is actually pretty well known as a standard result in quantum mechanics. For our particular wave function, now at t equal to 0, psi xt is given by just the incident part, psi 1 xt. And when t is much bigger than t0, psi xt is given by the sum of psi 2 and psi 3, since, as we have already argued, psi 1 vanishes there. So, the conservation of probability would tell you that 1, the normalization of the original incident wave function psi 1 mod square dx is integral, must be the same as psi 2 plus psi 3 mod square dx is integral. This is for t much bigger than t0. And this is, of course, at t equal to 0, or in fact t much less than t0 will also do. Now, if you look at this integral, which is psi 2 plus psi 3 mod square's integral, you should get psi 2 mod square dx's integral from minus infinity to plus infinity, plus psi 3 mod square dx's integral from minus infinity to plus infinity. The first of these terms is actually what we know as R, and the second one, this integral, is t. However, there should be, in addition to this, a cross term. The term given by psi2 star psi3 plus psi3 star psi2's integral over all space from minus infinity to plus infinity. Now this seems to cause a problem with our relationship that t equals 1 minus r. But note that in our particular case, there is no chance of a problem because psi2 and psi3 are non-zero over different ranges of x. Psi2 has a theta minus x with it, psi3 has a theta plus x with it. What that means is that they are non-zero for negative x and positive x respectively, and their product is always 0. So this term is 0 by the very way in which psi2 and psi3 are set up. So r plus t has to be equal to 1. And therefore, our relationship t equals 1 minus r is perfectly justified. Since the r that we had obtained directly by integrating psi2 mod square dx a while ago agrees exactly with the time independent Schrodinger equation approach. The only thing is the k has to be replaced by k0, the mean momentum of the wave packet. The t would also agree with the corresponding first year result. But it would be nice if we could actually directly calculate psi3 mod square dx's integral and verify that the t we get exactly matches that result. And that is what we are going to do in the rest of this lecture. Note that this part is strictly speaking not necessary because the argument that we have already given tells us exactly what t is, but it's satisfying to be able to work things out in detail. Also note that this is perhaps the only part of this lecture which is substantially different, apart from some calculational details, from what Shankar says in his book. This part is actually relegated to a problem in Shankar's book. Shankar does not explain how this is done. So let us now dive into the calculation of t directly from the definition. Integral of psi3 mod square dx. Now, since it has been some time since you have seen the full psi, you may have forgotten what it looks like. So let me remind you, this is our entire psi at x comma t, of which this piece gives me the first term, psi1, this piece gives me the second term, and this is the one which we are looking at now, the third piece. C by a e to the I k prime x theta x, multiplying this integrated over k. That's our psi3. So let us try to collect the terms together for that. If you look at psi3 and psi3 alone, what you get is sigma squared by 4 pi cube to the power 1/4, of course. The theta of x being a constant independent of k can be brought out of the integral. That's what we have done here. This overall factor in the momentum wave function comes here. The time dependent part is here. And finally, you have e to the I k prime x. Along with it, of course, you have c by a, which is a function of k dk. K prime occurs in our integral in two places, once inside c by a and again directly explicitly here in the I k prime x. And this k prime is given by square root of k square minus twice mv0 by h cross square. Now this integral, of course, is not really a Gaussian integral, both because of the fact that the c by a factor messes things up a bit, but also because of the presence of this nonlinear term in the exponent. K prime is not a linear function or a quadratic function of k. Well, the first thing that we can do is tackle the issue of c by a being a function of k, and we tackle it in essentially the same way that we did for psi2. Since the real part of this exponent here is just given by minus sigma square by 2k minus k0 whole square, this tells us that as far as size is concerned, the integrand is peaked very, very sharply around k equal to k0 with a width of around 1 by sigma. And so, What we can do is replace C by A at K by its value at K0. Exactly what we did with B by A in our previous example. And we can then of course pull it out of the integral. We are now left with an integral which looks almost like a Gaussian integral except for the presence of this e to the I k prime x term. But there also we will use the same kind of argument. Since the expression has a e to the power minus sigma square by 2 k minus k0 whole square, thus making its value die out very rapidly when k is far away from k0, we will just expand every term here in the exponent in powers of k minus k0 and retain up to only the quadratic power, ignoring the higher order terms. So when you expand this, we can of course expand this term rather trivially, writing k as k minus k0 plus k0. This is exactly what we did for Xi2. And this is just the binomial theorem, or the formula for a plus b whole square. The slightly non-trivial part is writing ik prime x. This is ix times square root of k square minus twice mv0 by h cross square. The k square can be replaced by exactly the same thing as here. And the k naught square minus 2mv0 by h cross square is the term which you get when k is equal to k0. These two terms dying out then. We will call this quantity k0 prime square, which is of course just the statement that k0 prime is the value for k prime when k is k0. Pulling out the k0 prime square from the square root, I get I k0 prime x times this expression. 1 from here, twice k0 by k0 prime square into k minus k0 from this term, and k minus k0 whole square by k0 prime square from this term. This whole thing is raised to the power half. K0 prime of course is nothing but the square root of this. The next step would be to actually just use the binomial theorem, but this time for a fractional index, for an index of half. Let me just remind you that for a power of half, 1 plus x to the power half works out to be 1 plus half x plus half into half minus 1 minus half by 2 factorial x square and so on. Since we are going to work only up to the quadratic power, that's all we will need. So, I k0 prime x times this expression becomes 1 plus half of this, which gives me this and this, plus minus 1/8 times the square of this. Now, when I'm squaring this, I don't even need to look at the full square, I just need to square this piece, because that's going to give me the quadratic term. All other terms are going to be higher order. So we just stop here with 4 k0 square by k0 prime to the power 4, k minus k0 whole square here. And this is of course a minus 1/8. Now we can just rewrite this slightly by multiplying by I k0 prime x, and I get I k0 prime x, the 0th order term, plus I times k0 by k0 prime x into k minus k0, the linear term, plus if you just do a bit of algebra here, rather trivial algebra, you get I times k0 prime square minus k0 square by twice k0 prime cubed into k minus k0 whole square. So collecting everything together, the exponent becomes the following. I write this term as it is. IKA I write as IK minus k0a plus IK0a. This one is exactly the a plus b whole square formula that we have seen before. And IK prime x is replaced by this, the thing that we had just worked out. So now let's collect terms together. The k minus k0 whole square term has a piece from here, here, and of course here. So when you collect all of them together, this is what you get, with a factor of minus half thrown in outside. Actually, I think this will be a plus, because we have taken minus half outside. And I've already switched the sign here. The linear piece works out to be this one, and this one. That gives you the three pieces. And finally, the constant term works out to be I k0 prime x. This is a term which is independent of k minus k0, k0a, and of course this term. So that's the full expression for the exponent up to quadratic powers in k minus k0. This looks pretty complicated, but frankly, much of it will be simplified in the final calculation. All we note is that the sigma squared has been replaced by this whole factor, which I'm going to call sigma tilde t whole square. It depends on t. Of course, it also depends on k0, k0 prime, m and h cross. But time dependence is what we are focusing on right now. It's a function of t, and its value at t equal to 0 is of course sigma square. What is also important is to stress, this is something we are going to need later, that the real part of sigma tilde square is simply sigma square. This part being purely imaginary. Similarly, this expression we can also write as this part, the linear powers coefficient, we can also write as k0 by k0 prime x plus a tilde t. A tilde t being a minus h cross k0 t by m. So now, our expression for psi 3, the integral that we have to do, boils down to the following. Theta of x sigma square by 4 pi cube to the power 1 4 c by a at k0. These are all what we had. The exponent in the integrand is now minus sigma tilde t whole square k minus k0 whole square. So this is my a for the Gaussian integral. This term is the b. And this is the c. So using our result that we had already derived earlier, this is what the integral evaluates to. This of course is an approximation for two reasons. One being that we have replaced the c by a at k by c by a at k0 while evaluating the integral. The other being that the exponent has been approximated. The k prime in the exponent has been expanded only up to quadratic powers in k minus k0. Note that in both cases, this is a very well justified approximation because my wave packet is bound to be narrow in k space, centered rather sharply around k0. Of course, in addition to this, you also have this whole factor, which just comes out as a constant, e to the power c. So this is my transmitted wave, which can be seen slightly differently in the following manner. All I have done here is just move the k0 by k0 prime out of this bracket. And what that shows us is that this effectively is a Gaussian whose center is given by x0 is minus k0 prime k by k0a plus h cross k0 prime t by m. This is pretty easy to understand. It just says that the center of the wave packet is moving with a speed given by h cross k0 prime by m. Remember, to the right of the barrier, or rather to the right of the step, the wave number is given by k prime, or for the wave packet the mean wave number is given by k0 prime, and therefore h cross k0 prime by m gives me the velocity of the center of the wave packet, which makes this term easy to understand. With a bit of thought, you will be able to realize exactly why the constant piece, the time-independent piece in the center's coordinate is given by minus k0 prime by k0 into a. This actually ensures that the wave packet actually enters the positive x region only at the time t0, when the incident wave packet has come and hit the barrier. This is of course, an important part of the wave function. It tells us that the wave packet is actually moving with the momentum given by h cross k0 prime. But for the rest of our calculation, which will involve psi t mod square, this being a pure phase will not really be that important. So now, let's calculate t directly. We take psi t mod square dx integral from minus infinity to plus infinity. Of course, we do this only as t is much bigger than t0. At this point, calculating this integral is really rather straightforward. The only thing that we have to remember is that psi t mod square has a theta square x, which is of course the same as theta x, which ensures that this integral is not carried out from minus infinity to plus infinity, but only from 0 to infinity. Then you have to take the mod square of this, those are straightforward. This is the mod square of 1. The only thing we have to be a bit careful about is when we take the mod square of this. So we have e to the power minus this k0 by k0 prime square x plus a tilde t whole square by twice sigma tilde t square. Its mod square will involve multiplying this quantity by its conjugate. So you will have the same kind of thing, e to the power minus exactly the same thing, except that in the denominator you will have sigma tilde t star square, conjugate of sigma tilde t square, and when you take that into account, this is what you end up with. I just moved the k0 by k0 prime square from the numerator to the denominator here to sit along with the sigma tildes, but the sigma tildes essentially change into this quantity, 1 by sigma tilde t whole square plus 1 by sigma tilde t conjugate squared. Now this is simply the sum of these two quantities divided by their product, and that means it's twice the real part of sigma tilde t square by sigma tilde t mod to the power 4. Now this is a standard Gaussian integral which can be immediately evaluated, and what you get is the following. Sigma square by pi sigma tilde t to the 4 to the power half, that's the factor that you had already, c by a mod square, times pi over a, and that boils down to, after you cancel out these two 2's, k0 prime by k0 whole square, sigma tilde t to the power 4, again the modulus of sigma tilde to the power 4, real part of sigma tilde t whole square to the power half. Now you can see that there are lots of cancellations. These pi's cancel, the sigma tilde mod to the power 4's cancel, and because the real part of sigma tilde t square is sigma square, these two also cancel. And at the end of the day, what you end up with is that the transmission coefficient is simply k0 prime over k0 times c by a mod square. That is 4 k0 prime by k0 plus k0 prime whole square, which can easily check is 1 minus r. To summarize, the calculation that we had done in our very first quantum mechanics course, which gives us a reflection and transmission coefficient, may have been conceptually faulty, but it does give you the right results, since, as we have seen today, carrying out a more careful calculation involving starting with a wave packet, allowing it to evolve in time, and analyzing what it turns into at very large positive times, does give you exactly the same results. The only difference, of course, is that because we are dealing with a wave packet where the energy and hence the momentum is spread out slightly, you have to use the central momentum values h cross k0 and corresponding h cross k0 prime to calculate the reflectance and the transmittance. Now that you have seen the more precise calculation, I'm pretty sure you would also appreciate why, in a very first quantum mechanics course, a student is not exposed to all these details, but rather given access to an approach which actually allows you to get the right result with a lot less fuss. That being said, it's still very important to be aware that there is a more precise approach, And frankly, this more precise approach is not really that complicated. It can still be understood as long as you're prepared to work slightly harder than usual. With this, let me call it a day today. Bye.